So today we're going to take a look at section 2.6, which is called related rates, and just some guidelines to start out with about how to think about these types of problems. It's often helpful to make a simple sketch if it's appropriate. Many of the times our problems are going to have some sort of a visual that'll make it a lot easier to solve if you draw something out for yourself. There's almost always going to be, not almost always, always going to be an equation that you're going to set up relating the relevant quantities that you're given and that you're asked to find. We are going to differentiate implicitly with respect to time. That's different. Prior to this, we've been differentiating implicitly with respect to x as a variable. Now we're going to do this with respect to time. We're going to substitute in known quantities and known derivatives, and then solve for the remaining rate. All right, so just a real simple example, just verbally related rates. How fast you drive is directly related to how quickly you get to school, right? It is. That's a related rate kind of quantity. Those two things are connected, and they're rates. They're how something changes, all right? So that's the idea behind what we're going to be doing. We're going to be looking at quantities that relate to one another and looking at how they change, as how one of them changes as a direct result of the other one. All right, so we're going to start with one. And most of the time our images that we end up with are going to end up being images that we're very familiar with. So let's take a look at this one. It says a fish is reeled in at a rate of 1 foot per second from a point 10 feet above water. At what rate is the angle of elevation, theta, between the line of the water changing when there is a total of 25 feet of line from the end of the rod to the water? So, I don't know how familiar we are with fishing, but the imagery is going to be the same whether you're super familiar with it or not, all right? So we've got someone. You can draw him if you want. I'll draw him. This is as good as my people get right there. And he's fishing, right? So he's got a fishing pole. There's his fishing pole. And the fishing pole is got a line out here somewhere in the water. So there's my fishing pole line. It says that he's 10 feet above water, so that's why I've drawn him sort of high up. And here's my water line down here. So he's probably on some kind of a bridge or a dock or a boat, all right? So that's how he would be 10 feet above water. So this is 10. Everybody good so far? What image did I just draw? It's triangle, right? There's nothing like cryptic about what's going on. Once we put the image to it, we recognize certain geometric shapes. This is a triangle. All right, so let's see what else we've got. He's reeling in his fish at a rate of 1 foot per second. So this is his fishing line, right? And the fishing line's length is changing. So whatever letter you want to represent, we'll do it in a minute here, it's going to be changing and it's decreasing, right? He's pulling the fish in at a rate of 1 foot per second. The angle of elevation between the line of water. So angle of elevation, here's my water line, and angle of elevation would be this one right down here, theta. Theta is changing as well. So think about what happens as he's pulling that fishing line in. The guy's not moving. He's stationary. So what's happening is this line is actually becoming closer to him like this. Can you imagine that? Okay, it's creating smaller and smaller triangles, basically. And so that angle of elevation is changing, right? That theta is actually being increased as it moves in, right? This is the theta value, and it's increasing as it moves in. Okay, so I don't have a whole bunch of triangles, but my triangle shape is changing. Are you good with that? Okay, let's see what else it said. It says, at what rate is the angle of elevation changing when there is a total of 25 feet of line from the end of the rod to the water? So there is a point at which there's 25 feet of line out there. It's a single point in time, right? Because the guy's changing this length of his fishing line at a constant rate. So it's not happening that it's always 25. It's not constant. Are you with me? The 25 is not a constant quantity. It is a specific point in time when it will be 25. It's also changing. So let's take a look at what we have here. We've got our angle, theta, and we've got this length right here of our fishing line. Those are the two things that are changing. What's the known quantity? The 10, right? The known quantity, I didn't draw it very well, but imagine that this actually went up to where his fishing line was, because that's where it should be going up to, right? This is 10, and it's not changing. So I need something that will relate my 10 that's not changing with my theta that is changing, and my, how about we just call it x here? My x, my length of my fishing line, that's also changing. So I need something that relates those three quantities, an equation that relates those three quantities. Any idea what that would be? What's that? Okay. Well, let me just tell you, it's trig. Sine. You're right, Dylan. Dylan, right? Damon. Oh man, I am just struggling today. Damon. You're right, Damon. Yes, it is. It is sine. So what makes you think of it as being sine, Damon?
The opposite side from the theta over the hypotenuse.
Yeah, good. So what we remember from trig is that the sine of theta is the opposite over the hypotenuse. And those are the pieces of this particular triangle that I know. I know the opposite side, and it is a constant. I'm going to fill this in 10. It never changes. I do not get to fill the hypotenuse in as 25. It is changing. Eventually, I'll evaluate it at 25, but it's a changing quantity, so this is x. And then the theta value is also changing, right? So my original equation is going to say sine of theta equals, oops, 10, right, over x. That's the equation that I'm going to differentiate. Is that good so far? What if instead of knowing the angle or talking about the angle, we were looking at how the sides related to one another? What equation might you set up here if you were looking at the side relationships of this triangle? What? Tangent still relates an angle to two different sides. Pythagorean theorem would be a good choice. So when you're dealing with triangles, either tangent, sine, and cosine, or Pythagorean theorem are usually where we end up with our equation from, depending on what quantities we're trying to relate. Does that make sense to everyone? Okay. So we need to take the derivative here now. So, starting with the left-hand side, what's the derivative of sine of theta? Cosine of theta. But do you remember when we were working with implicit differentiation, we then have to take the derivative of the angle theta. And we're doing it now with respect to time, which means it's d theta dt. How is theta changing with respect to time? We know it is, right? We do. This might be helpful to write this way, so I'm going to do that real quick. 10x to the negative 1. What's the derivative of 10x to the negative 1? All right, good. Negative 10, x to the negative second. But then I need the derivative of x. And we didn't have to do that last class period because dx was 1. Remember that? But I'm not doing things with respect to x. I'm doing it with respect to time. This x, this length of the fishing line, is changing with respect to time. So it is a dx dt. It's chain rule. I've got two chain rules, a chain rule on each side, because each of the variables themselves is also changing with respect to time. So far, so good. Okay, I'm going to clean up just a little bit. I have cosine of theta, d theta dt is equal to negative 10 over x squared dx dt. And if we've done things right, at this point, we should be able to evaluate all the pieces we know, like substitute them in, and solve for the piece that we don't. So do you know theta? No. We'll come back to that in a minute. Do you know d theta dt? Nope, but you're close. The 1 foot per second is not d theta dt. What is it? It's dx dt. So it is a rate, it's just the other rate, because it's not how the angle was changing, it's how the fishing line was changing. Yeah, so I'll put that in there. So this one is actually -1. Do you know what x is? It's 25. Right? It wants to know what's happening at a specific moment in time, i.e. when x is 25. Now let me go back to our triangle. At this specific moment in time, I know these two quantities, right? They change in general, but at this moment in time, I know these two quantities. Can I find theta? I can. How would I find theta? Tangent of theta is 10 over 25, right? Grab your calculator. You're going to need it. So theta is the inverse tangent. In radians, please. Always radians for calc. And the more decimals you keep for the moment, the better. So I usually recommend at least 4 as you're working through the problem, and then we round at the end. What'd you get?
The tangent cannot be 10 over 10.
Oh, I did not mean tangent. I'm so sorry. I meant sine. My bad. I got carried away from when we were talking about it before as being something we can use. It is sine. Thank you so much. Should say sine. Inverse sine of 10 over 25. So what is the inverse sine of 10 over 25? 0.4115. So over here now, I have the cosine of 0.4115 d theta dt. It looks ugly, but there's only one thing I don't know. D theta dt, right? So I can solve for it now. So I have, let's see, on the right-hand side, this is now positive because I have -10 and -1. That green is almost unreadable. How about purple? That's better. We will have d theta dt equals 10 over 25 squared, and then divided by cosine of 0.4115. It should tell you within WebAssign how many decimals to use. For now, let's just keep going with 4. What did you get for this particular rate? Okay, we'll go with 7.5. Very good. All right. Is that what you have?
One is negative because you're not, it's like going backwards, right?
Yes, exactly, because it's decreasing. That's a very good question. I don't think I made comment about that. This is a -1. I'm sorry, I didn't mark it that way because it's decreasing. The length of the rope is decreasing, or the fishing line is decreasing. Yeah. Okay, we need some units on this. Any idea what the units might be? What is it? 8? Feet. Not feet, because this is the angle, right? We're going to have radians, yeah, the angle right here. So the way that you decide on your units, the units on dx dt included feet because they had x in them. But this one actually has theta, and it has time. So theta's on top, time's on bottom. So how is theta being measured? You said it, Eric, in radians, right? Yeah, so this is radians. And then the time is being measured in seconds, so radians per second. So my best suggestion to you is to remember the quantity that you're deciding you're finding, and that's always being given to you right here, right? I'm finding d theta dt, and then use that to give you a reference point for finding your units. All right, you want to try another one?
Yes.
Yes. That was decisive. Thank you so much. All right. So if you have any related rate problem on a test or a quiz for me that is triangle related, I'm not giving you any formulas. You should know what sine, cosine, tangent, and Pythagorean theorem are. Those are all straight out of trig that everyone's completed and done well in at this point, okay? So that's something you wouldn't get for me. However, this next one is one that if I wanted to use it, I'd give it to you because it's not so common. All right, so this one says a spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? So what are the quantity, well, let's draw a picture actually first. What's the picture I'm going to draw? A balloon. Sure. So there's my balloon. I get to cheat because I have tools. Yeah, I know it's not fair. And our balloon needs to look, you know, three-dimensional. So something like that. So that's a good first drawing. We've got a balloon going on here. So what are the quantities that we're relating in this balloon? Like what's going on? Ignore the rate part in a moment. What does it reference?
Radius.
The radius. So I need to mark the radius. I'll mark that on here. And the radius is changing, right? So there is a change in the radius going on, kind of like my fishing line and my angle in the last problem. They are changing. But eventually the radius value that I'm going to be using is going to be 30 centimeters. I'm even going to write the word eventually here because I don't want you to think that that's constant. It isn't. It's changing. What else is changing as a result of the radius? I know it looks kind of funny, but do you know what this is actually measuring? It's the volume. The volume that the balloon holds is changing. So do you remember, this is one I'm telling you, I don't know that I would remember necessarily off the top of my head if I were in your shoes. Does anybody remember the volume of a sphere? Do you?
Yeah, it's 4/3 pi r cubed.
Wow. Very well done. It is. If I gave you this problem, I'd give you the formula, okay? So don't fret about that. But that is right. It is 4/3 pi r cubed. The volume's changing. The radius is changing. Everybody good with that? Cool. And this quantity right here that they're telling us is how the volume is changing, yeah? So this is actually dV dt. It's how the volume is changing with respect to time. Cubic centimeters, right? Centimeters cubed, cubic, right? Per minute. All right, so we're going to take a derivative of volume, or of this volume equation. So the V right beside on the left-hand side at the moment is all by itself, which is always very friendly to have it alone. Over on this problem, it's less than friendly because it was always connected with something else. On the left-hand side, it was an angle inside of the sign value, and on the right-hand side, it was something underneath the value of a fraction. But volume right here, oh, I meant over here. That's what I was trying to show you, sorry. But over here, volume is a standalone quantity. So when we did dy dx before, every time y was alone and we wrote down dy dx, that's how this volume is going to be. The derivative of volume is dv dt, all by itself. V doesn't go away, but derivative of V would be 1 dv dt. That's what's happening there. What about 4/3 pi r cubed?
3 times 4/3 pi times r squared.
Okay, there's one more thing I need. I mentioned you can figure out what it might be. Thank you. Yeah, so again, R is a quantity that's changing with respect to time. So we had all those pieces exactly like we had back when we didn't have to worry about the other variable, in this case, the other variable of time. But now since R is related to time as well, we get dr dt. And that actually is very nice over here, ends up being 4 pi r squared. And very well done, Emma, on recognizing that pi is just a number. So just like the 4 sticks around, the pi sticks around as well. It's a constant multiplier. I don't have like a product rule or anything like that there. It's just by itself sticking around. So dVdt, drdt, and r. Which of those quantities do I know? I know dVdt, it's 800. And I think my balloon's increasing, yeah? So the volume is actually positive, right? So it is increasing. If it were being deflated, I would have a negative 800 here. What else do I know? The radius at a specific point in time, and this is now the time to use it, it's 30. So I have 30 squared for the radius. All right. So we're going to do some calculations. Let's see, 30 squared would be 900. 900 times 4, 3600 pi. And I've got 800 on the left. Oops. drdt. So what would I do?
You could, do you want us to leave pi or do you want us to add pi into it?
That's a really good question. I'm glad you asked it because I didn't think to answer that question. We want to have answers to application problems in usable form, which means they will be approximations and they will be decimals. Okay? So it doesn't make sense to talk to somebody and tell them this in terms of pi. I understand it's more accurate, but it isn't usable information. Does that make sense? So we are going to round, and WebAssign or your test or your whatever you're working on should indicate how many decimals. If it doesn't, we'll just go with 4. That's what we're going to say right now. 4 is our go-to unless it indicates something different. So I will divide though, right, Emma?
Yes.
Yeah, so I have 800 divided by 3600 pi. The one thing to be careful about if you're doing that division in your calculator is to make sure that you're putting the 3600 and the pi all together in a set of parentheses. Because if you just put it in from left to right without parentheses, your calculator will likely think 800 divided by 3600 and then multiply by pi, all right? So you do want to make sure that you're careful on that. If you do that, what will you get? Again, it is approximate, but what do you got?
0.0707.
Excellent. Now let's think about units. R, what's that?
Is it R per second?
It is per second, but what is R? Centimeters. Good. So it's centimeters per second. Radius is in centimeters on this one. I'm not second. It was minute, wasn't it? So bad. Second was my last problem. Thanks. Okay, cool. All good? Okay, I have one more example for you. I tried to pick 3 different shapes that showed up to give you some perspective of how they might appear. A lot of ours do show up in triangle form, so be encouraged by that. Oil spills out of a tanker at a rate of 90 gallons per minute. The oil spreads in a circle with a thickness of 1/8 inch. Determine the rate at which the radius of the spill is increasing when the radius reaches 100 feet. So, what shape is this creating? It's a cylinder, right? It's a really thin cylinder, right? Think about a puddle on a ground. There's thickness though, right? So yeah, it's a very thin cylinder. You don't have to draw it super thin because then it becomes difficult to mark on it, but it is a cylinder. Like so. All right, this 90 gallons per minute business, I'm going to have to give you some information on that. How did I write that down? All right, so 1 cubic foot is equal to 7.5 gallons. Okay, so that's one of those things that there's a conversion here we're going to have to make in a minute. But 1 cubic foot is actually 7.5 gallons. All right, so let's find out what we actually have. There is something here that's constant. Can you tell the piece that's constant?
The cylinder.
The height of the cylinder, right. The height of our cylinder is 1/8 of an inch. It's very, very small. But it is a constant here. We have this 90 gallons per minute business. What is that? What does it represent? It's obviously a rate, right? It's changing because it says gallons per minute. It's changing, it's a rate.
It's going out of the tanker 90 gallons.
Yeah, so it's the amount of oil, right? And if we're measuring the amount of oil, we're talking about volume. Are you with me? That's a volume. So this is an argument about volume. So dV dt here is 90. And right now I have gallons per, what was it, minute? Yeah, minute. But gallons is a volume measurement. It's not a cubic measurement, right? Like the last one, it was in cubic centimeters. So I need to get it into a linear measurement that's been cubed, which is why I gave you that information at the top of the screen about feet. And I don't know how much you've done with conversions before. Conversions can be done very nicely as like a multiplication by a fraction. Since those quantities are equal, that is the cubic foot and the 7.5 gallons, I can write down 7.5 gallons on bottom and then 1 cubic foot on top, and I can turn this into cubic feet per minute instead of gallons per minute. So grab your calculator. What is 90 divided by 7.5? What is it? 12 cubic feet per minute. All right. And then it talks about radius here as well, yeah? I think that's the only other piece I don't have marked yet. So let me write my radius in here. My height I didn't mark yet, but there it is. The radius is changing though, right? The oil is thick. It's staying at a 1/8 consistency, right? It's just leveling out as it continues to pour. But the radius is changing, so that's not constant. But eventually the radius is going to be what in this problem? 100 feet, but this is changing. I just want to make sure we keep the changing versus the constant things clear. All right. 2 things to do. First, I need a volume formula for a cylinder.
Pi r squared times h.
Very good. Volume is pi r squared, which you should recognize as the area of a circle, right? And then times h gives me volume for a cylinder. Good job. And then I also have one more sort of issue on my screen. Does anybody see what it is?
Okay, so you have to make sure that the units match up. You have feet cubed and just feet by itself.
Okay, that's true, but that's not a concern quite what I'm getting at. We do have feet cubed and we have feet. There's something else though. There's inches on there. Do you guys see that one? This inches is actually the problem. The feet cubed and the feet's going to work itself out with the multiplication that takes place because I'm going to have feet multiplied to give me feet cubed. The inches, however, is a problem. However, inches are related to feet, obviously. So we have to decide, do we want to work inside of feet or do we want to work inside of inches? You want to do feet? So we need to change our 1/8 inches into the number of feet that it actually represents. So let's get that next. So again, I can actually make a ratio. How are feet related to inches? 12 inches in 1 foot. So this is going to be a very small number, but I need 1/8 divided by 12. 0.0104 feet. Okay, pretty good so far? Okay, now the piece that's actually constant, the height, can be plugged in as the height before I start taking any derivatives because it's not changing, 0.0104. It's not a variable, it's constant. Everybody good with that? But like I can't plug in R is 100 right here. That's not appropriate because R is changing. So the pieces that are constant can be evaluated right away. The pieces that are changing need to hold off on until the very end. But we can take a derivative now. So we did this before with V. What's the derivative of V? dv dt. And then I have 0.014, 0.104 pi, and then what's the derivative of r squared? 2r, ooh, somebody said it, dr dt, yes. So here's another thing too. You better have two rates, because the whole problem section is related rates. So if you only have one rate when you get to this point, you've missed something. You've missed something. Related rates. There better be two rates at the end of the problem before you start evaluating things. All right, and there are now. We have them in there correctly. All right, dv dt, do we know that one? We do. What is it? 12, right? 0.0104 pi times 2. What's r? That's my 100 now. And dr dt is the quantity that I do not know. All right, grab a calculator. We got a lot of mess here, but we can handle it. In essence, I need 12 divided by 0.0104 pi times 2, well, times 200. I can at least do that part in my head. dr dt. So what will dr dt equal here?
It's supposed to be really big.
1.83.
That's what it should be. You probably have forgotten some parentheses. Yeah, or make sure it's really easy to forget, but make sure when you're dealing with this denominator that all of it gets divided or multiplied together before you do the division with some parentheses. Say that again, Emma.
1.833.
Can you do me 4 decimals?
5.
5, yeah. 1.8335, and we need units. So again, we look back here. What do you have, Emma? What were you about to say?
Okay, so if you just keep, or if you put everything in, like to your equation,
Yes.
with the units, you can just easily cancel them out.
Yeah,
And
you'll
make
see them
sure
cancel.
that
Mhm.
they're all right.
Yeah, you're right. So if the 12's in here, it was 12 feet cubed per minute, right? And let's see, my radius here is 100 feet. And then this one right here was also in feet. So you have, come on, give me another color. Feet and feet canceling with 2 of these feet, so to speak, and we have 1 foot left. You're exactly right. You can also look at it at the end if you want to not use the units through the middle. That's how I always do mine, but it's okay to do it the other way. And you can see that you've got dr on top, and the units on r are feet. You have t on bottom, and the units on t are minutes, right? So this is feet per minute. All right, this assignment has WebAssign and written homework. Do you see that at the bottom of your page? There are 3 written homework problems. We will turn those in on Thursday. I know a couple of you have talked to me. Chat with me again if we haven't cleared up how you'll get that to me if there's a conflict with you being here on Thursday. But turning those in on Thursday. We also on Thursday will be doing what? Has anybody looked? Huh? Nope, not another quiz. Review. We're done with chapter 2. All right, we are reviewing on Thursday, which means what are we doing on Tuesday? Tuesday is a test. That's exactly right.